Hey everyone, welcome back. Today we're going to be looking at expectation values
Oh, yeah.
in quantum mechanics.
I love expectation values.
Yeah, they're really cool. They're kind of like,
They're like a tool
Yeah.
that we can use to predict the average outcome
right.
of measurements in the quantum world.
Even though things can get pretty fuzzy down there.
Yeah, exactly.
Mhm.
In quantum mechanics, you see,
Yeah,
we can often not say for certain
right.
what the outcome of a single measurement will be.
Yeah.
It's all about probabilities,
Yeah.
but these expectation values give us a way to make sense of this probabilistic world,
Okay.
to see the bigger picture.
So instead of knowing exactly where a particle is,
Mm-hmm.
we can kind of figure out where we'd most likely find it
Yeah.
if we
If we look a bunch of times.
looked a bunch of times.
Exactly.
Yeah.
Think of it like trying to figure out the average height of students in a class.
Okay.
You wouldn't just measure one student
Right.
and call it a day.
Right. You'd measure a bunch.
You'd measure a bunch of them, take the average.
Yeah.
Expectation values are kind of like that,
Okay.
but instead of heights, we're dealing with things like a
Yeah.
particle's position or momentum or energy.
Okay, that makes sense.
Yeah.
But how do we actually go about calculating these?
Well, it's a bit more involved than just taking a simple average.
Okay.
We use mathematical tools called operators,
Okay.
which represent the physical quantities that we're interested in.
Okay.
And then we combine those operators with the system's quantum state,
Okay.
which is like a snapshot of the system at a particular moment in time.
Okay, hold on.
Yeah.
Operators. Quantum states. This is starting to sound a bit complicated.
Don't worry, it's not as intimidating as it sounds.
Okay.
Just imagine the quantum state as a set of instructions
Okay.
for how the system behaves.
All right.
And the operators are like tools that let us extract specific information from those instructions.
Okay.
And by combining them,
Yeah.
we get the expectation value, which tells us the average outcome we'd expect to see for a particular measurement.
So the expectation value gives us a prediction for the average outcome of a measurement,
Yeah,
even though we can't know the exact outcome of any single measurement.
precisely. And here's where it gets even more interesting.
Okay.
These expectation values can actually change over time.
Oh.
Kind of like watching a movie unfold.
Yeah, so the average outcome we would expect can actually shift as the system evolves.
Exactly.
It's not just like a fixed value.
It's like watching the average height of our class of students change as they grow older.
Oh, okay.
The system itself is dynamic, constantly evolving,
Okay.
and its expectation values reflect that.
Wow, that's mind-blowing.
Yeah.
So how do we track these changes over time? Do we just keep recalculating the expectation value at different points?
Well, there's a more elegant way.
Okay.
The evolution of a quantum system is governed by something called the Schrödinger equation,
Mm-hmm.
which is like a script telling the quantum particles how to move and interact. By applying this equation to the system's quantum state,
Yeah.
we can see how the expectation values change over time.
So the Schrödinger equation is like the director of our quantum movie.
That's a great way to think about it. It's like having a behind-the-scenes look at how the quantum world unfolds.
Wow.
And by understanding this equation, we can predict how the average outcomes of our measurement will change as the system evolves.
So it's like we're not just predicting the future,
Yeah,
but we're actually like watching it happen in real time.
you're catching on quickly.
Thanks.
Now, as we watch this quantum movie unfold,
Yeah.
the time derivative of the expectation value depends on a few key things.
Time derivative.
Okay, let me put it this way.
Okay.
The rate at which the expectation value changes depends on how the operator,
Okay.
which remember represents the physical quantity we're interested in,
Yeah.
interacts with the total energy of the system, which is described by something called the Hamiltonian.
So it's like a tug of war between the specific quantity we're measuring and the overall energy of the system.
Exactly.
Okay.
And sometimes the operator itself might change over time, which adds another layer of complexity to the mix.
Really?
It's like our measuring stick suddenly expanding or contracting while we're trying to measure the height of our students.
So even the way we measure things can change in this quantum world.
It is indeed.
That's pretty wild.
But even amidst all this change and complexity,
Yeah.
there are some things that remain constant.
Okay.
We call them constants of motion. They're like the bedrock in this constantly shifting quantum landscape.
So some things in the quantum world stay the same. It's not all chaos and uncertainty.
Exactly. These constants of motion provide a sense of stability.
Okay.
They're like those dependable friends who are always there for you no matter what.
Yeah.
And they play a crucial role in our understanding of quantum dynamics.
So what makes something a constant of motion? Is it just like random chance, or is there a deeper reason.
There are actually two specific conditions that need to be met for a quantity to be a constant of motion. First, the operator representing that quantity shouldn't change over time.
So the way we measure it stays consistent.
Right.
Okay, what's the second condition?
Second, the operator needs to play nice
Okay.
with the Hamiltonian.
Okay.
It's a mathematical way of saying that they don't interfere with each other's actions.
So they work together in harmony.
Precisely. And when these two conditions are met,
Yeah.
the expectation value of that quantity
Okay.
remains constant over time.
So it's like a North Star
Exactly.
in our quantum world, always pointing in the same direction.
Exactly.
I'm trying to wrap my head around this idea of these operators changing over time.
Yeah.
It feels like the rules of the game are shifting as we play.
Yeah.
Could you give me an example of when that might happen?
Certainly. Let's say we're trying to measure the position of a tiny particle that's zipping around in an electric field. As the electric field changes, it influences the particle's movement.
Right.
So the way we describe its position would need to adapt as well.
So the concept of position stays the same,
Yeah,
but the way we measure it has to adjust to the changing environment.
exactly. And this time, dependence of the operator adds another layer of complexity to how the expectation values evolve. It's like our quantum movie now has special effects, adding new dimensions to the story.
Okay, so we've got these expectation values changing over time, governed by the Schrödinger equation, and some quantities stay constant, like the North Star.
Exactly.
But where do these stationary states fit in?
Yes.
I remember you mentioned them earlier.
Stationary states.
Those waves that wiggle but don't move forward.
They're kind of like the musical notes in our quantum symphony.
Okay.
They have a well-defined energy.
Okay.
And while their phase might oscillate, their overall shape remains constant over time.
So they're kind of like humming a constant tune.
Yeah.
Even though they're wiggling back and forth.
That's a great analogy. And because their shape doesn't change, the probabilities of making different measurements in a stationary state also remain constant.
So even though we're still dealing with probabilities, at least the odds stay the same.
That's right.
In these stationary states.
Stationary states are the building blocks of quantum systems.
Okay.
Even the most complicated quantum systems can be thought of as a combination of these simpler, more predictable states.
So it's like breaking down a complex dance routine into a series of simpler steps.
And this allows us to understand the evolution of even the most complex systems by analyzing how their individual stationary states behave.
So these stationary states are like the foundation.
You could say that.
Of everything else that happens in the quantum world.
Now, remember how we talked about the phase of a stationary state oscillating?
Like the wave is wiggling but not moving forward.
Well, even though this phase oscillation doesn't affect the probabilities of different measurements, it plays a crucial role in how the system evolves over time.
So even though the notes stay the same, the way they're played can change the whole tune.
It's like the conductor's baton guiding the orchestra through the symphony.
Wow.
This phase, information is encoded in the mathematical description of the quantum state. And it's essential for understanding how the system unfolds.
It's incredible how much depth there is to these concepts.
I know, it's fascinating.
We started with this idea of a quantum crystal ball.
Yeah.
And now we're talking about symphonies and conductors.
And we've only just scratched the surface.
This is truly mind-blowing.
It is.
I'm starting to see how quantum mechanics is not just about weirdness and uncertainty. There's a lot of order and structure hidden within it.
It's a beautiful balance, isn't it?
It really is. So we've covered a lot of ground today.
We have.
We've learned about expectation values, those predictions of average outcomes in the quantum world. We've seen how these values can change over time, guided by the Schrödinger equation. We've explored the constants of motion, those quantities that provide a sense of stability amidst all the quantum fuzziness. And we've delved into the world of stationary states, the building blocks of quantum systems.
Indeed, we've taken quite a journey.
Yeah, it feels like we've gone from peering into a quantum crystal ball to listening to a grand symphony.
It does.
But I have to admit, there's still one thing that's nagging at me.
What's that?
If some quantities are conserved, those constants of motion we talked about, does that mean the future is in some ways predetermined?
That's a really profound question, and one that has puzzled physicists and philosophers for ages.
Yeah, I bet.
It's true that the existence of these constants of motion implies a certain degree of predictability in the universe.
Okay.
If certain quantities remain constant over time,
it suggests that the future state of a system is constrained, at least partially, by its present state.
So even though quantum mechanics is all about probabilities, those conserved quantities give us some hints about what's to come.
Exactly. It's like knowing the rules of a game.
Okay.
Even if you don't know the exact moves a player will make, you can still predict certain outcomes based on the rules.
Right.
In a similar way, these conserved quantities provide a framework for understanding how quantum systems can evolve, even if we can't predict every single detail with certainty.
That's a really helpful analogy. It's like those conserved quantities are the underlying structure of the universe, while the probabilities are like the unpredictable events that play out within that structure.
You got it's a delicate balance between order and chaos. Between predictability and uncertainty. And that's part of what makes quantum mechanics so fascinating.
This has been an incredible journey. We started with this seemingly simple idea of expectation values.
Right.
And we've ended up pondering the very nature of predictability in the universe itself.
It's amazing what we can uncover when we start digging beneath the surface, isn't it?
Absolutely. It just goes to show that there's always more to learn.
Yeah.
Even in the seemingly most bizarre corners of science.
I couldn't agree more.
Well, thank you for guiding me through this fascinating exploration.
Oh, of course.
I feel like I've gained a whole new perspective on quantum mechanics.
It's been my pleasure. I always enjoy sharing these mind-bending concepts with curious minds.
Thank you for listening to Podcast Learn and Fun. We hope you enjoyed the journey of learning. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.